Okay, let's get started. Good morning, everybody. Uh, let's share my screen. Could you see my screen?
Yes, sir.
Yep.
Okay, great. Um, as you know, in last class, I mentioned about instrument transformer and then auto transformer. So today, at first, we'll be looking those concepts. Uh, as you can see by the name instrument transformer, it is being treated a device or apparatus and that can measure high voltage and current. And there are two types of instrument transformer. One is called current transformer. It is abbreviated as CT, and then potential or voltage transformer, abbreviated as PT. So that's the thing, that to measure the high voltage and current, you can't use the simple laboratory ammeter or voltmeter because those are the high voltage and high current. So definitely you need the help of transformer. So those are that current and potential transformer. So therefore, let's take you to that whiteboard, then you will get it. Okay, so let's first discuss that current transformer, CT. How does it look like? So for example, your line is going on. Sorry. Your line is going on, and then along the line, you put a transformer. This is the line. And I want to put a transformer because I want to measure the current flowing through this line. How much current is flowing here? So that's why I am putting a transformer. This is on side, and then this is the other coil, secondary coil. So that side is primary and this side is secondary. So, and then at the secondary side, I am putting a ammeter. I want to measure the current on the secondary side. So I connected ammeter. Also for the safety purpose, this is properly grounded. Now, everybody say, so could you guess what should be the rating of this transformer? Is it 10 ampere, 5 ampere, or 1000 ampere? Could you guess something? So therefore, definitely it is not like that. I mean, a small transformer. That is the first guess. But you see, you can use those small transformer, small rated transformer like 5 ampere, 10 ampere, provided that for this transformer, this is the high voltage side. This is high voltage side and this is the low voltage side for this transformer. Because if this is high voltage side, then definitely current will be lower than this side. So you remember that relationship like V1 over V2, that actually I2 over ion, and that equals to N1 over N2. That's the relationship. So if you say that this side is V1 and then this side is V2, current here is that is the I2, this side current is ion, this side turn ratio is N1 and this side is like N2. So therefore, if this side is high voltage, then if you say according to this relationship, then you will be getting low current in this side. And that's why I am putting a small rated ammeter. So everybody, do you understand? So therefore, this is a transformer. This is that current transformer that will measure the high current. So therefore, high current is flowing along the line. So therefore, the thing is that you cannot directly connect a ammeter here along this line. That's the thing. You cannot connect because high current is flowing through this line. That's why you are taking the help of a transformer. This means this side should be low voltage, this side should be high voltage. Accordingly, you have to design so that the current is much lower in this side. And then once you get the ammeter reading from here, so to know the current in the actual line, then you use this relationship. I2 over I1 equal to N1 over N2. So then you are getting the current here. So do you understand what I said? Everybody is fine?
Yeah, it makes sense to me.
Yeah, we're good.
Yeah. Therefore,
Wait, I have a question about the actual, like, I guess, structure of it. Doesn't it just like a service wire like go through like the current transformer is like a ring and it just goes through it?
Yeah. So therefore, for example, as I was telling you that, okay, this is the line going on, like high voltage line. Here, along the line, you have to put this transformer.
Yeah, but it's just like a ring that the wire goes through.
Yes, exactly. Right. Just rim, I mean, wire goes through it. Yeah. But just, just the important thing is that you have to make this side high voltage. Therefore, with the help of the turn ratio, you have to maintain that. So that voltage in this side is very high. So therefore, now there is some precaution. You understand that, okay, I got the small current here, and by applying this technique, I got the high current here. That is fine. But then can you guess that because this side is very high voltage, so it is the personal safety issue. The technician or the engineer who is measuring the current here, so he or she should be very careful because it is the high voltage here. And then sorry.
So it does actually work like a transformer where, like, current goes up, voltage goes down, current goes down, voltage goes up.
Yes, exactly. But for this case, it is not like that frequently with because this is on the line, along the line. So it is not like that frequently someone will go up and then come down with the help of the ladder. Typically an ammeter is connected there. And then you will get automated reading in the control center. For example, MLG control center, they will get the automated reading here. Now the thing is that, for example, somehow you need to take out this ammeter. You need to disconnect this ammeter. Either for it is not giving good reading, or it is not working, or for some maintenance reason. For example, you need to uh, take out this ammeter for some reason. Then what is happening? If you take out the ammeter, then the secondary side, because this is high voltage, it is fully open. So therefore, this situation is very dangerous. I mean, the current flowing through the primary side, because this is line, but no current flowing through the secondary side. Consequently, you see, the energy flow is not balanced between these two sides. So there will be a very high flux density. So therefore, magnetic core will be highly saturated. It will be overheated, and even transformer may be burned. And easily you can guess that it is the personal safety issue. So that's why it is recommended, if you want to take out the ammeter here, if you need to take out the ammeter for some reason, so before doing that, first you have to make a switch. Therefore, typically there is a switch. It is called that sorting switch. It is called sorting switch. It is that sorting switch. So this means that before taking out the ammeter, like initially your ammeter was here. So before taking out the ammeter, first you sort this, first you close the switch. Then it is safe. Now if you take out, you see, now I took out, but the secondary is not open. So that's why there is a switch here. This switch is called the sorting switch. Typically it will remain in that, it is in the open status when the ammeter is connected. Now, for some reason, if you need to take out this ammeter, then first connect this one, and then you take out the ammeter, so that the secondary is not open circuited. So that's why it is highly recommended for a city that secondary circuit should never be open circuited, because secondary side has high voltage, it's personal safety issue. Plus, when it is open circuited fully, then the current is flowing through the primary. The primary coil is magnetized, but in secondary current is not flowing. So energy balance will not be maintained. Consequently, the core there will be high flux density in the secondary. Core will be gradually magnetized and heated up, and even it may be burnt up. That's why the high precaution that secondary side should never ever be open circuited in case of a CT. Okay, and then let me save this one. Okay, and then now in case of the PT, let me delete this thing. That is the CT. Now,
Before we move on to PT,
sorry, what you said?
I was going to say before we move on to PT, I had a question about that, but
Okay,
I
oh,
guess-
sorry. Oh, what is the question?
I guess that first one where you show the transformer is like the turn ratio, like one of them doesn't have any turns and then the other one does because the straight wire is going through the CT.
No. So before placing on the line, so properly turn ratio is maintained. Properly it is calculated. So that because you have to make secondary voltage very, very high so that you get very small current.
Mm-hmm.
Accordingly, it is designed before placing it along the line. Basically, it is the connection in the line, the primary coil.
What do you mean the connection in the line?
So your line is going on, for example, in that way. It was the line, right? And then you make 2 point. This is one point, this is other point. Here you will be placing that coil, the primary coil.
Yeah, you're saying that's the line.
Yeah, that's the line, yes. And
And
then this is the secondary coil. So therefore, before placing along the line this system, then you have to properly calculate that what should be the number of turns here on the
Yeah,
secondary coil, so that it will show much higher voltage than this one.
yeah, but the primary coil is just the line. It's just that wire.
Yeah, yes.
Cool. That's what I was wondering. Thank you.
Yes, okay. So I mean, definitely, you know, along the line, you already have what is the voltage, right? Amount of voltage, you already know.
Mm-hmm.
So therefore, accordingly, when making this one, you will properly calculate the very high value of the voltage so that the current value becomes smaller, like only 5 ampere or only 10 ampere.
Mm-hmm.
Okay, great.
Thank you.
Okay. The next one, PT, the potential transformer. So because it will measure the voltage, for example, you are measuring the voltage, this is on and then this one is the neutral. You want to measure the voltage of this line, high voltage, with the help of a voltmeter. So again, you need transformer. So this time you put a transformer. This is the primary, and then this is your secondary. And then here you connect your voltmeter at this point and at this point. And then again, for the safety purpose, make it properly grounded. So therefore, definitely you can guess that this side should be the high voltage side and this side should be the low voltage side, so that this voltmeter reads very low value of voltage. And then again, you know, with the turn ratio, V1 over V2 equal to N1 over N2, you will get what is the, you will get what is the voltage on the high voltage side. And then because this is the line going on, it is going on, you have to assume that the loads are connected here in parallel. These are the loads are connected, but between the lines here, between this line and then this neutral line, so you can connect a transformer to measure the voltage. So therefore the condition is that the point where the technician will go or lineman will go or engineer will go, they will measure the voltage from the low voltage side. And then by using this equation, they will find out what was the voltage here. So therefore this is the phi t. So here there is not that much precaution. So everybody, could you follow me? So how to measure the high voltage along the high voltage line with the help of a transformer? So look, this is a transformer, primary side, secondary side, but this side should be the low voltage side. Accordingly, you will build this one. And then you just measure the voltage on this side. And then by applying this one, you can get what is the voltage in this side. That was your point of interest. You want to know what was the voltage, high voltage along the power line or the high voltage line. So this is called the PT, I mean the potential transformer or voltage transformer. Okay, so I think everybody got this one. So now again, go back to the other discussion. Okay, so therefore we understood those two. Now you see, auto transformer. Auto transformer, what is that? It has a single winding, part of which is common to both the primary and secondary simultaneously. So you see, this is pretty interesting. It has only one winding. It does not have two windings. And the same winding is sharing both the primary and secondary. And what I said, it is extensively used to interconnect two high voltage transmission lines operating at different voltage. So therefore, for example, one line has 345 kV, and then the other line, subline or some intersection line has 115 kV. In that case, those auto transformer is used. So I am showing you the diagram. I am drawing the diagram. So this is for the application for the high voltage transmission line. But in our real life also, you can understand about this auto transformer. So let me take you once again there, and then you will be getting that. Okay, let me delete these things. Okay, so for example, you have a coil, and then I applied the voltage. This is my primary side voltage, and it has a number of turn, which is N1, I said. Now, from here, make a tapping. This side, for this side is V1, this side is V2. And then here that current flowing was I1, here the current flowing is I2. So therefore here, the number of turn is N2. And then the whole thing is from here to here, the whole number is N1. So therefore from here to here, that is the remaining term, like N1 minus N2. So everybody, could you see? There is only one set of coil. Whatever the total number of turn is, there is one set of arrangement. And then to get the secondary voltage, I am just making a tapping from this point. So therefore, it depends on the requirement. For example, just an example, okay, if you have the 100 volt here, that appear across the full coil, and then for example, here it is just a random example, 50 volt. Now, in order to increase the voltage here, definitely then you have to make tapping from here, for example. Or if you want to increase the voltage here, or if you want to decrease this amount on the secondary side, then you have to make tapping from here. So in that way, it is the same coil, but it is sharing to both the primary side and secondary side. So this is that's why it is called the auto transformer, because the coil is common to both the primary and secondary. So everybody, do you understand this one?
Yep, makes sense.
Yeah, great. So now I can give you one real example. First, let me clean up. Okay. I can give you one real example of this one. Everybody, like, you have the ceiling fan at your home, but probably you have not seen that there is a regulator to be equipped on the wall to control the speed of that ceiling fan. I think you have not seen that one, but typically have you seen this thing? Does anybody have that control mounted on the wall to control the speed of the fan? Does anybody have? I mean, typically what happens, you have the ceiling fan and you have a string. With the help of the string switch, you turn on and turn off. And then there are three speed there, like the highest speed, medium speed, and then low speed. And then you can turn off. But there are other type of ceiling fan on which there is a, the control switch. This control switch is mounted on the wall. And then from here, with the help of a regulator, typically there is a knob. It is just the tap setting. You will just tune it. For example, here it is 120 volt. In this position, it is like 100 volt. And then here it is 90 volt. It goes in that way. Just control. And then accordingly, ceiling fan speed will decrease or the increase. So that is the best example of the auto transformer. So this means for the ceiling fan, that is the voltage regulator. And that is an example of the auto transformer. The other example is that soon you will be going to the lab. I mean, this week you are going to the lab, but you will start your actual experiment in next week. So at that time, you will be seeing a device that is called the Variac. That is called Variac. VRIAC. That Variac variable AC. That Variac is another best example of auto transformer. With the help of the Variac, basically, you will be controlling the voltage level. This means, for example, here on the primary side, when you are using the full coil, then it is 100 volt. Secondary side, at this position, you are getting 50. Then you can change the tapping. No, I want to get more voltage. Probably at this position from here to here, you will be getting 80 volt. And then again you increase. And even you may go up to, you may use the full winding. So this means primary and secondary is the same. Or you want to decrease the speed of your fan. So, okay, make the tapping here. Maybe it is only 30 volt. So just by controlling some knob setting, there is one circular device called the Variac, or that voltage regulator in case of a ceiling fan, you can control the tapping on the secondary side, and then definitely your ceiling fan is connected with the secondary circuit. In that way, you can control the fan speed. So therefore, Variac is a good example of the auto transformer, and then which definitely you all will see in the energy conversion lab.
Dr. Ali, are we also going to talk about VFDs in this class?
What?
Variable frequency drives?
Oh, yes, VFD, definitely.
Okay.
I think that will be experiment number 4, probably. Yeah.
Okay, thank you.
Yeah, no, most welcome. So definitely, I mean, right after the transformer, I will start that induction motor chapter. Induction motor, it is called. For example, I was referring to the ceiling fan. So do you know the name of the motor in the ceiling fan? That is actually single phase induction motor. And to control those type of motor, you need a variable frequency drive. Variable frequency drive, basically a power electronics device. But in the lab that you will be doing, that is the three-phase system, three-phase induction motor. So I'll be covering those things in next chapter. So therefore, I think you all understood this one. So now then, once again, go back there. So see, in case of the transmission line, this is the application that auto transformer is extensively used to interconnect two high voltage transmission line operating at different voltages. So just to make two separate circuits. Yeah. Okay, then now on important thing, it is called transformer polarity or dot convention. So what is that meaning? I mean, in a minute you can understand. So once again, I need to go there. Okay, let me clean off all of these things. Okay, so the first of all, like transformer polarity concept or the dot concept, this is on coil, and then this is the other coil, secondary coil. Typically, you will notice even in the lab, it is marked in that way. The name of the terminal H1 to H2, and here it is like X1 and X2. So typically, the high voltage side is designated by the symbol H. So this is H1, this is H2. And then like here, you will be applying the voltage. So this is the high voltage side. Okay, and this side, which is marked by symbol X, letter X. X is typically used to indicate that this side has the low voltage. Now, you will see another thing that sometimes it is marked dot. The dot is here, and then dot is here. So those dots are used to indicate the current flow. For example, this dot means current is entering at this coil. This dot means current is leaving on the secondary coil. Like this is I2 and this is I1. So you see the dot meaning here that current is entering at this terminal, and this dot means current is leaving this terminal. But sometimes, or sometimes it is designated by plus minus and then the plus minus. So you see, if it is plus minus, then definitely, I mean, you are measuring the voltage with this polarity, plus minus. Similarly, here plus minus, you are measuring or you are applying the voltage here. Now, sometimes, those dot marks are not given, or the plus minus signs is not properly mentioned, sometimes incorrectly placed. To know that, to find out the correct polarity or the correct dot terminal, you can make a simple test. Therefore, for example, so everybody see, to make a test, you just need a voltmeter. For example, you have a voltmeter and you may connect that voltmeter between this point and then this point. You connected the voltmeter, and then everybody see what I am doing. You make a short on those 2 points of the two transformer. And then, for example, you applied high voltage, some voltage here. For example, you applied high voltage here. So everybody see, I marked that this was the plus sign here, this was the minus sign. And also I have proved that, okay, this is the plus sign and this is the minus sign here. Okay, and then you want to make sure that, okay, I have put the correct polarity. I have correctly placed the plus minus on this side. That's why you are making a test. Your voltmeter is here and you have made a short. Now, for example, if it is 100 volt and you got the low voltage here, for example, this voltmeter gave you 100 volt rating. Or for example, you got the higher voltage. It was 100 volt here. But for example, this voltmeter gave you 120 volt or even much higher voltage. So you might face two situations. Either this voltmeter will give you lower rating than this one, or it can be the higher value than this one. So therefore, now you tell me, for example, you got the lower value than this one. Then what does that mean? Was the polarity correct? Was plus minus here? Was it? Or the minus should be here, plus should be here. In the other hand, when you got 120 volt through this voltmeter, then was it right? Was it plus here, minus here, or it should be minus here and plus here? Everybody, could you follow what I am asking?
Yes, yes.
Yeah. So therefore, I mean, I want to verify. I want to making sure that I placed plus minus here. Is it correct or not? Polarity transformer, polarity marking, correct or not? That I'm trying to find out. And then that's why I applied 100 volt here. And then you remember, so this I just make shorted. This means I throw a wire, I just connected these two terminal, and I have added a voltmeter between this point and this point. This point now, these two coils are in series fully. And then I got higher rating. So what does that mean? Should it be plus here, minus here, or the minus should be there and then plus should be there? On the other hand, when you are getting the lower rating, then should it be plus or the minus? And then the opposite will be here. So therefore, I mean, I think you will be getting that point. So guys, how you connect the battery? For example, you have two 1.5 volt battery, for example, and then plus minus, and then plus minus. So this means that this is on like 1.5, and then this is another 1.5 volt battery. Then what will be the reading? It will be 3 volt, right? Like plus minus, plus minus. Sometimes you connect the battery in that way, then it will give you the 3 volt. But if it is like plus minus and then the minus plus, then ultimately you will be getting the 0 volt because it is opposing. This is on battery and then you connect the other battery. So in that way you will get 0 volt because that is not additive, that is subtractive. In this case, like plus minus, then you might add another battery in series. Then it will increase your voltage. Do you understand what I mean? So therefore, everybody say similarly. So if I say it was my minus plus here, everybody see the same. It was plus here, and then I short circuited here. So if it is minus here and then plus is here, then it is operate like, you see, minus plus and then the minus plus. Then you will get higher rating, this reading. On the other hand, when it is plus here and then the minus here, this means that this is minus plus and then the plus minus, then you will be getting lower rating. So therefore, when you are getting lower rating, you will be telling that, okay, this is the subtractive polarity. And when you will be getting higher rating than this one, this means it is the additive, it should be the additive polarity. It should be the additive polarity. This means minus should be here, plus sign should be here. Does this make sense?
Yeah.
Yeah. So, I mean, just think about, that's why I mentioned about the battery example. Think about the battery. How you connect is, for example, you want to connect three battery in series. How do you do that? Properly you maintain the plus minus sign, right? Plus minus, then another plus minus. Then it will give you, like, if it is 1.5 volt battery, then 4.5 volt, or in this case 2 battery 3 volt. But if you connect in opposite way, then your circuit will not work. Whatever the device you are using, it will give you the zero voltage. In other words, it is the subtract. That is the meaning. So that's why this transformer, that polarity marking, sometimes, I mean, you are not worried in our laboratory. Sometimes in real practice, that polarity marking is important. That's why I am discussing that point here. Okay, so now moving forward. So we covered this one. Now, you see, I mean, last class, we are discussing that efficiency of transformer, and I wrote down this equation, and this is a pretty common equation that you use. And we'll be using the similar equation or exactly the same equation to find out the efficiency for motor generator as well. So this is a pretty common equation, like output over input, but input means output plus losses. If you know this information, then you can easily calculate the transformer efficiency. Now, what I am discussing here now, so instead of efficiency, you see, I have used another terminology, all day efficiency. All day efficiency. So what does that mean? So you see, I have written for you that in contrast to power transformers, distribution transformers operate well below the rated power output most of the time. Therefore, their efficiency performance is evaluated based on all day or energy efficiency, which is defined below. So you see, all day efficiency, I have written energy output over 24 hours taken as a percent of energy input. So here I have used the word energy, but here I simply use like output input. So this means that in this case, it is just the output power. It is the input power, but it is the energy output over 24 hours. Now the thing is that, you know, think about your house. In your house, 24-hour power consumption is not the same. It varies. In the morning, for example, if you consume 1 kilowatt, then in the noon, for example, if you are cooking, just an example, then that will increase. Again, in the afternoon, maybe some decrease. In the evening, when you turn on all the lights, probably that will increase. I mean, it depends on the customers pattern, or customers the life, their lifestyle. So it depends. So for every family, it could be different. So that's why never ever in a distribute. So customers, we are connected to the distribution transformer, not to the power transformer. Power transformer means those are placed along the high voltage line, but distribution transformer, which are pretty close to the customers, those operate well below the rated power output most of the time. Because as I mentioned, it depends on the customer's behavior, customer's lifestyle, customer characteristics. Someone use high power in the morning, but someone may use in the night, someone may use during noon. It depends. So this means 24-hour you are not consuming the power equally. That's why distribution transformer are not overrated. They run well below the rated power output. That's why you cannot say what is the actual output power. You go in terms of the energy output. So the energy means power multiplied by the time, power multiplied by the time. And then you calculate for 24 hours and what was your energy input over the 24 hours. So that's why it is called the all day efficiency. Now, why I am emphasizing this on, if you see some examples or solve problems in the book that we are following, or in any book, or in any power system book, you will see that this term, all deficiency, or one or two problem you might face about the all deficiency. So that is this one. That's why I'm taking. Just keep in mind, it is in terms of the energy, not in terms of the output power. Okay, then moving forward, you will be finding on phenomenon or on concept which is called transformer inverse current. This is very important. So just you can have a look what I said. When a transformer, whatever it is loaded or unloaded, is suddenly energized, then a transient phenomenon occurs due to magnetizing current characteristics, producing very high magnetizing current. That could be 8 to 10 times of the transformer rated current. And such high current phenomenon is called inverse current. And it is advisable to use a line reactor when energizing a transformer. So let me explain. So first of all, once again, everybody have a look. This means when you are attempting, for example, a transformer is at rest, it is not working initially, and suddenly you energized. Suddenly you connect the primary of a transformer to the actual lines. That time, a transient phenomenon occurs, meaning that the magnetizing current could be very high, as I said, 8 to 10 times. I mean, then gradually it decays. Always it will not be like 8 to 10 times. After, over the time, it will go away. It will be decayed. That phenomenon is called inverse current. And how to handle that? You have to use a line reactor, oil energizing a transformer. So what does that mean? So then once again, let me take you to that whiteboard. Then you will be fine. Let me clean off all of these things. So what we are talking about, just for example, this is a transformer, for example, that's just I'm drawing in a box format. And this is the three-phase terminal of the transformer. This is transformer. And now you had these lines. Okay. So therefore, this is A phase, B phase, C phase. And then these are the three lines, like line 1, line 2, and line 3. And then, for example, for the operation, you suddenly connected those transformers, this one. So if you suddenly energized, if you suddenly powered this transformer, and then of course, there is secondary on this side. So then what happens? That is the phenomenon. For example, I am plotting the current, magnetizing current for this transformer. So for example, it should be the normal value, for example, but then because of this transient phenomena, current goes very high, very high. And then after that, what happens? It gradually decays. And then, you see, this is called the transient phenomena. Therefore, for example, this should be the rated current, but then it goes, as I told you, 8 to 10 times. I mean, in fact, it might go much higher. Just I'm showing you an example. So this is the first transient, then subtransient, and then ultimately it becomes normal. But when it happens this transient, the current is very high. So therefore, this transformer might be damaged. So therefore, that is not suggested. Don't do that. That okay, you directly connect and suddenly energize a transformer. So what you have to do? You have to do before connecting this one. So you need to connect some small reactor. That is the meaning. For example, connect some sort of reactor. Connect some sort of reactor. So if you have some reactor ready, and then if you energize, then probably it will go a little bit, but then quickly it will settle down. The reason is that you see, these are the these are the inductor, a small reactor. So then can you guess, I mean, why this reactor helps to mitigate this transient or to reduce this magnitude? Or what is the property of an inductor? What does an inductor do for a circuit? So therefore, across a inductor, current can't change instantaneously, immediately, right? That is the property. And then similarly, what's the property of a capacitor? Through across a capacitor, voltage can't change instantaneously. That's why you know that capacitor is used in a rectifier circuit. Always there is a capacitor to provide a smooth DC. And in this case, we are using the inductor to work as a limiter, to work as a transient mitigator, transient the decay component. So because through a inductor, current cannot change immediately or instantaneously. That's why it is safe. A little transient may happen, but it is not like that 8 to 10 times. So that's why this is highly recommended. Before energizing a transformer, please use some small reactor. That is the meaning. Could you follow me?
Yep, makes perfect sense.
Yes. So this, you might face this question in the FE exam, in your FE exam, that what is the way or what is the recommended way to energize a transformer, or whatever it is, loaded or unloaded. It does not matter. What is the way? What is the safest way? Then you would be answering this on, we have to energize the transformer with the help of a reactor, which is an inductor, just to mitigate, just to reduce the magnitude of transient current, initial transient current. That is called that inrush current. You see, transformer inrush current. And then we will be looking same thing, same phenomenon in case of induction motor, three-phase induction motor. Because three-phase induction motor, that will be, I mean, starting soon. So three-phase induction motor principle and transformer principle is exactly the same. Just in case of motor, it will rotate, and transformer is not rotating. Transformer does not have any moving parts. That is only the difference. But the working principle will be the same. That's why that is called the induction motor. And then same phenomenon we look at, and we will be applying the same solution. We have to put, or we have to use a line reactor when energizing a induction motor. The same thing we will be looking. Okay, so now moving forward. Today we will finish this chapter, transformer chapter. Now, three-phase transformer connections, you know that so far we discussed mainly the single-phase transformer. But you know, in real practice, there are three-phase transformer and single-phase transformer both. But then once it is three-phase transformer, you know, the all concept, everything, calculation process, all are exactly the same as the three-phase circuit that you all have already learned. So now, for example, here you see, I have written three-phase transformer can be connected in different configuration. So, you know, this is on single-phase transformer. BB, this is another single-phase transformer. And then this is another single-phase transformer. Now, there are three separate single-phase transformer. And then from these three separate single-phase transformer, I want to make a three-phase transformer. So that is the question, that how to connect. This is one single, another single, another single. And I want to make three-phase transformer. That I will be looking. So now depending on the requirement, you see I have written here, primary could be Y, secondary could be Y. primary could be Y, secondary could be delta. Primary delta, secondary Y, or primary delta, secondary delta. So this means that you see the number 1 and number 4, both sides like YY, in this case, both side is delta delta. But then number 2 and 3 could be different like Y delta or the delta Y. So these 4 are the possible connections for a 3-phase transformer. And then always what happens, especially in case of delta Y or Y delta type, number 2 and number 3, there will be phase difference of 30 degrees between the Y side and delta side voltage. In case of the YY, there will not be any phase difference. In case of the delta delta, there will not be any phase difference. Only the voltage magnitude will be different. But in case of the Y delta or the delta Y, there will be a 30-degree phase difference. Now the thing is that how to make connection. Like you have these 3 separate single phase transformer. How we will make them 3-phase? So therefore just let's have a look, some example. For example, I am making YY. So this should be the primary side, this 3 coil, and this 3 coil should be on the secondary side. And because this is Y, so that's why I will have the provision of the neutral. So you remember the 3-phase circuit previous chapter? You connected the neutral line in case of the Y system, not with the delta system. That's why, because here I am showing you the 3-phase YY transformer connections. So that's why there is neutral both on the primary side, on the secondary side. Now see, you have to make Y. How it is done? Is this point, this one is connected with this one. And then again, this is the other. So this means, you see, if you say this is one first terminal, then second terminal, first terminal, second terminal, first terminal, second terminal, then to make the Y, all second terminals of all 3 coils are connected together. This one, and this one. They all are connected together, and then the rest are the 3 lines, one line, second line, second line and the third line. You remember that how to make Y? This is the symbol Y. So this point is the common point. So this means all 3 things are connected together. And then from that common point, that neutral line is going. The same thing on the secondary side. This one and this one and this one is connected together, and then line is going neutral. And then you have 3 terminals open through which you will measure the voltage. So therefore, this is the 3-phase YY transformers. Now, how you will make the delta? Look this one. You see, you have to make this connection. This means there will be a common point between 2 phases. There is a common point between 2 phases. So how to do that? You see, this is first terminal, this is second terminal for this coil. So second terminal is connected with the first terminal of this coil. Again, its second terminal is connected with the first terminal of this one. And then this C is connected with A. And then this is the 3 terminal. So then like you make that delta connection. Same thing on the secondary side. Everybody, do you understand how to make connections, how to make delta? Does it make sense?
Yeah.
Yeah.
Yes, it does.
Yeah. So just you think about like how you connect the delta. Like delta is this, right? So just look the symbol. Delta means there should be a common point between 2 coils or the 2 phases. The same thing. So this one and this one is this point. For example, this point. Then this one is this one, this point, this point. And then how we'll make the top point? So therefore, this one is directly connected with this one. And then you have to, because 3-phase system, you need 3 terminal that will go to the line or to the device. That is this 3 terminal. So you will be measuring voltage here, here, and here. The same thing goes for the right side, I mean the secondary side. And then this is the example of the like y delta. Therefore, because again the same connection, this point, and this point. In case of y, 3 points should be connected at a common point. And from that common point, you will be taking neutral. So therefore, because this is y delta, so that's why primary has the neutral, but secondary does not have neutral because secondary is the delta. The same thing. In this case, delta y. Primary could be the delta, secondary could be the y. Now you see, I mean, it depends on the application. I mean, those 4 types, delta delta or y or y delta or the delta y, it depends on the location. So therefore, you see, this system, delta y, think about like your home. For example, think about the locality or a industry. So therefore, industrial system, for example, industry may get power from the high voltage line. So therefore, that could be the delta side. But definitely, because customers will be connected, I mean, the loads will be connected on the secondary side. Therefore, it is preferred that the customer side or the load side has the Y connection so that you can connect the neutral. Do you understand? So what I mean? So therefore, delta Y should be placed for people use, for customers use. On the other hand, for example, the delta delta. From the delta delta, people cannot directly use the power because there is no neutral connection. So you cannot make it grounded. This is not the safe for the personal, for the customer. That's why typically delta delta is used along the high voltage line. Because you know that high voltage line is high power line, people can't use the power there. So instead of having the Y, I mean, you can put Y, there is no problem along the line and anywhere. The problem is that when there is very high voltage, very high power line, people can't use the power. So you don't need to use the Y connection because Y connection, you see, because Y connection requires the neutral line. So it is still a line. So it incurs some cost. So therefore, people cannot use power along the high voltage line. But then if you put this system, this means 1, 2, 3, and the fourth line in this side, like 1, 2, 3, and then the fourth. So therefore, this is just extra. It will just incur extra cost. And then people are not using. So therefore, in order to save cost for the neutral wire, typically delta delta is used along the high power line where people don't need to use power. So therefore, easily you can understand, for example, in a power plant, first voltage is produced and then right after the main generator, there is a transformer. Definitely that transformer has this configuration like with the neutral connection. But once it goes, along the long distance and along the high power and the high voltage line, definitely you can convert from Y into delta. So that's why, for example, this one, the Y delta. This is the one of the best example that, for example, this is nearby the power plant, this side, and then this side goes to the high voltage line. And then goes, and then fully this is delta, delta, delta. And then once again, people need to use power, then use this one, delta Y. So this means the left side was for the high power line, and again, you are making the Y side so that the people can use, customers can use the power. So accordingly, it depends on the situation and the location. That's why there are 4 types of transformer. Everybody, could you follow me what I'm saying?
Yep.
Yeah. I mean, just you yourself think about, why there is Y delta system, where to use Y and where to use delta. That thing I'm telling. Just you think yourself and then you will get the answer. And what is the necessity of, or what is the motivation of having this type of configuration, that thing I am telling. Okay, so now moving forward, I want to conclude this chapter, but then before that, for you, I have brought some short questions. So everybody please participate with me in answering the questions. And definitely you will be asked this type of questions in the upcoming midterm exams, final exams. And these questions are very, very vital for your like AFE exam as well as in your job interview. They will be asking this type of questions. Okay, so the first question, why cannot a transformer transfer DC power? So therefore, how would you answer this one?
I would say because an inductor is a shortened DC.
Exactly. So this means that like if you apply DC power on a transformer, then what is the type of the flux that will be produced? Is it constant or varying? It will be constant, right? If you apply DC power, I mean the DC voltage to a transformer, then it will produce the constant flux. I mean the DC flux. That is not time varying. Consequently, that DC flux can't induce or can develop any voltage on the secondary. And then in one hand, it can build up or generate voltage on the secondary side. The other thing, what will happen? Because you are applying DC power and the primary side current is flowing, and the constant flux will be produced, but that core will be magnetized and core will be heated up and gradually heated up, it is not doing anything on the secondary side. It is not producing voltage. You are not able to use. Gradually, the core will be saturated, core will be heated up, even might be burnt out. So that's why it is not advisable to apply the DC power to a transformer. So therefore, the answer is like that. First, you replied because the appropriate answer is because DC power will produce DC flux, and that cannot take part in developing voltage on the secondary. That's why transformer can transfer DC power. The question number 2, why is the efficiency of a transformer usually high? So how would you answer to this question? So we discussed that transformer has high efficiency, like more than 95%, close to 98%. What could be the reason? So therefore, if you think about the look this equation, everybody, efficiency, output over output plus losses. So therefore, there are two losses. One is called copper loss, another is called the core loss. But those are very small. So is there any rotational loss, frictional loss, bearing loss, or other type of loss in case of transformer? No, because transformer does not have any rotating parts, any moving parts. Because transformer does not have any rotating parts, so the amount of loss is very low, like only that is small core loss and some copper loss. So the amount of loss is very, very small. Mainly you will get the output. That's why efficiency is becomes very high. So therefore the answer is in case of a transformer, there is no rotating parts. There is no moving parts. Transformer is a static device. It has only two small losses, core loss and copper loss. That's why the efficiency is typically high. Could you follow me?
Yes, yeah.
Oh, great. So please note down the answers to your note. Yeah. Please write down the answers to your note. Okay. Now, question number 3. The primary and secondary coils of a transformer are separated, right? Whatever it is, core type or cell type of transformer, there is no direct connection between the primary and secondary coils. Then how does the secondary coil induce voltage? How would you answer to this question? So you see the question, there is no direct connection. They are separated. But then how does the secondary coil induce or develop voltage? What is the principle? So
Flux,
sorry?
magnetic flux.
Exactly. So you will be saying that Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. I mean, what you said is right, but just write in that way. Faraday's law of electromagnetic induction. And you remember, I think on the first class of the transformer, I wrote down some equation like E is proportionate to d phi by dt. This means if there is any changing flux, then according to Faraday's law, voltage will build up on the coil. You see, your coil is static. Like once again, transformer is a static device. Your coil is static. But then you need time varying flux. You need changing or alternating flux, magnetic flux in the core material. Then the voltage will build up. So now what is happening? Although primary secondary coils are separated, but they are mounted, those coils are placed on a magnetic material, core material. So therefore that core material is getting magnetized, and then that flux is changing flux, alternating flux, sinusoidal flux. Consequently, following Faraday's law of electromagnetic induction, voltage is getting induced in the secondary coil. Yeah. So you just note down in your paper or whatever better way you can express, you explain that one. But the keyword should be by applying Faraday's law of electromagnetic induction. Okay, got it. Number 4, why should not the secondary of a current transformer ever be open circuited? Why should not the secondary of a CT, current transformer means CT, ever be open circuited? So you remember what we were discussing with this question?
It'll be extremely unbalanced and dangerous. Yeah.
Exactly. Because if secondary is open, then the energy flow will be unbalanced. That's correct. And then also it will be extremely dangerous for the personnel, for the technician, lineman, engineer, or whatever whoever is working there. It is the personal safety issue. Because secondary will have very high voltage, and the core will be saturated because of the excitation current, and again the transformer might be heated up gradually. So therefore, please, you all mention all those points like that you said. There will be unbalanced in the energy flow because secondary side is open, and it is the personal safety issue. Plus there will be high energy flux density in the secondary, and it has the high voltage. Core will be saturated, gradually heated up, even transformer might be burnt off. That's why it is not suggested to have the secondary of current transformer open circuited. Always it should be open. So you remembered I was discussing, if you need to take out the ammeter from the secondary side, before taking out the ammeter, please connect the short circuiting switch. You remember I was showing on short circuiting switch. So first close that short circuiting switch and then take out the ammeter so that secondary is never ever open circuited. So you write whatever the best way you can write, but those should be the technical point that should lie in your answer. Okay. Now this one, question number 5. which transformer does use both conduction and induction principles for its operation? You remember that today we were discussing current transformer, potential transformer, and auto transformer. So among these three transformers that we discussed today, which one does use both conduction and induction principle for its operation? So think about the auto transformer. What was the feature in auto transformer? You remember? Auto transformer has only one common coil, only one set of common coil that is shared by both primary and secondary. So this means that it is also based on the conduction because it is common to both primary and secondary. And then definitely Faraday's law of electromagnetic induction is working because you are applying the AC voltage and your flux is changing, flux time varying. So definitely that is the induction, but then there is direct connection between the primary and secondary coil. So that's why that is the conduction as well. So that's why the answer is auto transformer uses both conduction and induction principle for its operation. Everybody, could you follow me?
Yeah, it makes sense.
Yes. So please you note down, write down the answer that auto transformer uses both conduction and induction principle. So great. So the last question for today, why is a transformer rated in volt ampere, not in watt? So therefore, this is very, very important question. The thing is that, I mean, in subsequent chapters, when we'll be discussing motor, generators, or whatever it is, AC motor or DC motor generator, always you will see that their rating is expressed in terms of like kilowatt or megawatt. I mean, simply in watt. But if you see the numerical problems that you already solved in this chapter, or last night I assigned you the homework, you will see the rating of the transformer. It is expressed in like kilovolt ampere, megavolt ampere, in that way, or in other words, in volt ampere, not in terms of watt. It is not never ever mentioned like 175 MVA 2400/240 volt transformer. Always you will notice that in terms of volt ampere, not in watt. So what could be the reason why it is rated in terms of that?
Is this
So,
because
sorry.
with apparent power instead of real power?
So the real power is the watt, and then apparent power is volt ampere. So what you said is Massa, Robert Massa is talking. Who was answering?
This is Sam.
Oh, okay, Sam. Okay. Please go ahead. What you said once again?
Yeah, no, I just said, is it because the transformer is rated in apparent power instead of real power? But
Oh, yeah. I mean, that is the question. That why is a transformer rated in volt ampere means apparent power that you are saying, not in real power. Yes, that's the question. Yes.
okay.
Yeah. Because the real power unit is what? Apparent power unit is volt ampere. So that is the question. So
When a transformer converts electrical energy, it's not perfect. So the small amount of losses makes it to where volt amperes is our measurement. And then after the losses, the true power that's left is the wattage, which is lower than the volt amperes.
yeah. I mean, so therefore your answer is like somewhat correct. So therefore you see what we discussed, like now think about the last class. In case of the transformer, what are the two main losses? What are the name of the two losses?
It's the core loss and I think with the coil loss.
Exactly. So therefore the core loss, everybody keep in mind, the core loss depends on voltage. And then the other one you said like coil loss, I would say the copper loss. Copper loss depends on current. Therefore, there are two loss in transformer, core loss and copper loss. And everybody note down in your note. Core loss depends on voltage and copper loss depends on current. Therefore, both losses depends on like voltage and current, not on the power factor. Core loss or copper loss does not depend on the power factor. That's why from that viewpoint, for its proper functionality, to take into account those two losses, only voltage and current information is enough. You don't need to think about the power factor. That's why transformer is rated in volt ampere, not in watt. Because volt is coming from the core loss, ampere is coming from the copper loss. That's all. You don't need to know the power factor. Because you see, power factor depends on the customers. Power factor of any load depends on the customer. It is you who will determine what type of load you are using at your home or at your building or in industry. If it is induction motor, then it has lagging power factor. If it is synchronous motor, then it might have leading power factor. If you are using a capacitive load, then it will have the leading power factor. If it is resistance, simply a bulb through which you are getting light, it is just resistive. It has no leading or the lagging. So therefore, this means the power factor, whatever it is leading, lagging, or unity power factor, all are dependent, all are determined by the customers. Transformer has nothing to do with that. So that's why transformer is always rated in volt ampere, not in watt. Because if it is watt, like as Samuel mentioned, like real power, so real power means VI cosine theta, and that cosine theta is the power factor. So therefore, that power factor belongs to the load, not to the transformer. So therefore, you will write the answer in that way, that a transformer has two types of losses. One is copper loss, other is core loss. Copper loss depends on current and core loss depends on voltage. Neither of the loss depends on the power factor. Power factor belongs to the load only. That's why transformer is always rated in volt ampere, not in terms of watt. So is everybody fine?
Yep.
Yes. And then, as I told you, these 6 questions are very, very important. Again, I will be asking you in any midterm exam or final exam. You will be facing these basic questions in your job market or in the job interview discussion, and highly likely that you will be facing in any of the question in the FE exam. Therefore, everybody, please try your best to understand, note down, and again, if you have any questions, you please ask me next time. Okay. Okay, so I think it's already 11. So although I had the plan to start that induction motor chapter, but I am not going to start, because if I start, then it will take a long time. So I want to conclude here today. So with that, does anybody have any questions or comments?
No questions.
Okay.
Everything makes sense.
Okay, thanks. And last night I sent out an email about the homework set too. Did you receive my email?
Yes.
Yes, sir. Have we
Okay.
covered so far that we need for the homework, or is there more lectures before we'll be able to do all those problems?
No, so yeah, as I said, I just concluded the transformer chapter. So you all are fine. You all are able to solve all the problems in the homework.
Okay, thank you.
Yeah, no lecture is remaining. So you just try your best and you see the lecture notes and see the videos, and then you are able to solve all the 5 problems. And I think I have the deadline is the next Friday, that 11:30 p.m. And I have created the Dropbox. Please upload your homework in that Dropbox. Okay, so with that, so everybody have a great and long weekend, and then see you on Tuesday.
Enjoy your weekend.
Okay, thank you.
You, bye.
Thanks.